So now it's a talk will be given by in presence here by Serena Sapio and online connection with Professor Andrea Taramelli and Dr. Margherita Righini from IUS in Pavia. Welcome. The title of the talk is Dynamic Land Cover Mapping Exploiting Satellite Images Insights on Large Raster Datasets Processing.
So thanks. I'm sorry that I cannot make in person, but I'm really happy, as already Nicola was saying, to have this, very wide approach, because at least from our side, we have learned a lot from very different topics. So if Serena share the presentation. And so I was already saying that as a group, we are fully involved in what is, the building up of the operational services that are using Earth observation data. And then we, in this processing testing we were doing, we were using what we have called the land cover dynamics as an essential climate variable to implement testing, how to set up an infrastructure. And so this was a preliminary work that was aiming at three main things. First, testing large dataset, raster dataset processing requirements to obtain what we call intermediate dynamic land cover products. This is done for determining the potential impact of which is the ICT infrastructure on largest dataset, and of course, defining what is the prerequisite to create a virtual machine into cluster the HPC use. And next, thanks. And I would like to set up what is the boundary condition. So why we are doing that? So one of the major issues that we are facing, at least in Europe, but is worldwide issues, is the fact that we have to go from research to operation. So I'm not going into details, but when we said downstreaming ecosystem, we goes from what is the data, so the Earth observation data, so what we all know that are satellite. But we start to face reality that we are building, and we already built a lot of satellites. So we are already delivering a lot of data. And there's a huge problem. This is a huge problem at European level, not only a national level, that we don't have yet good infrastructure to process this data and to produce operational services based on HPC infrastructure. This is a very huge limitation. I make a clear example, and then I will go a little bit on details, that in Europe we have the most imponent and biggest, not only program, it's a regulation, so it's a primary law that is called Copernicus, that is producing a giant amount of data and information, not only satellite data. And in order to implement analytics, most of the people, most of researcher, but also, and I was hearing also the previous presentation, most of the people are not using European HPC infrastructure. We are using Google Analytics, so we are using Google, Amazon, and so on. So we are spending a lot of taxpayer money to produce data and information in new satellite. And then the business, what we call the platform, the marketplace, is made by United States and Chinese. So this is a huge problem. So use is working, and there's some huge, let's say, funding grants right now, both from European level and from the next generation EU, so the famous PNRR, that are trying to figure it out how we can build the infrastructure that is going to be possible to use to do the data exploitation. So when we call about the data value, we are building what is called the downstream, so where the data is exploited. And right now, I really underline that European Union is producing the data. All the data are free, open, and free of charge, so everybody can can have this data. But most of the time, the marketplace and the infrastructure are made by countries outside Europe. and again, it's mostly United States and China. So this is a huge problem. So we take the chance to use this first, what we call seminal project, to start this type of analysis. And today we are going to present, a small example, but the next one, when we go from research to operation, we have to really understand what we are talking about. So when we talk about the Earth observation data, so satellite data, we are talking about like a specialized, quite extended data that really need also the in situ data in order to transform the, let's say, the raw data into value-added geospatial information that are, the one that are used from what we call the end users. I make a simple example. The National Civil Protection is using a lot of Earth observation data, but it has some issues that has to be solved. Next. So the idea is when we call and we discuss about pre-operational and operational products, we have to figure it out that we require automation for algorithm, for efficiency and timelines. I was making the example of the National Civil Protection because maybe most of the people doesn't know that when we call about the monitoring system of the Campi Flegrei in Italy, it's completely made by Earth observation data plus some in situ data. So the issue is also to have geographical coverage. We have to face also which is the latency to get this data. If we have to do emergency management and monitoring, we have to figure it out also what is the latency and what are the high priority and the high performance computing that allow us to have low latency. And then of course we have to set up infrastructure for spatial and temporal continuity and consistency. And then, of course, we have, facing the accuracy and temporal coherence between update of the products. Most of the issues also at European level with Copernicus is the fact that we are creating a giant, let's say, archive of what we call Sentinel, but it's too big. So the large-scale remote sensing data processing is already facing at European level that we are using what is the rolling archive. So if we do have to do monitoring for the extreme event and so on, we are facing already huge problem that we have not direct access. So we have to wait to to have access to the rolling archive. And this is a issue that the execution of sequential processing algorithm is rather time consuming and computationally expensive. Next. So, of course, we cannot do this with a desktop PC, but we have to set up infrastructure that account two major issues. And at the end of the presentation, you will see that our results is already setting up what could be, a baseline for the HPC, but also for the type of storage data that we need to do. Next. So I already introduced a little bit, but I'm happy to say that with the Next Generation EU, we have presented a national master plan in space economy. And so now Italy is complementing what is already available from Copernicus. And if you have never heard about Copernicus, please check it out because it's a giant amount of information. And Italy is funding and is, let's say, implementing and building a new satellite Iride constellation that is a multi-type of satellite. And the program is has the aim of building an end-to-end system consisting of low orbit satellite constellation, that is the upstream segment, but what is most important, the ground operational infrastructure, the downstream services. And this is the key part that we have started to study with this Rotary project, because at national level, there's never existed a ground operational infrastructure that allow, let's say, national civil protection, environmental monitoring protection system, and so on, to process this data in two major insight type. So Iride will offer, and by 2026, this will be all built 8 microservices related to marine and coastal monitoring, air quality, land movement monitoring, land cover, and so on. Again, just to make an example, most of you, I'm pretty sure, are using the Meteo app in each smartphone. Most of these Meteo app and also let's say air quality are based on Copernicus data and information processed at European level by entrusted entities like EC and WF, and now we are building this system at national level. So the ERLE system is going to be complementary to Copernicus. Next one. Before going to details, the idea, and I will stop with the next two slides, we have set up with this project. So we are building what we have called the Earth and Climate Innovation Hub in downstreaming services. So the idea is building up an environment where we support advanced research and development by providing regularly updated information. And to generate basically a development of what we called in the recent time digital twin. So the digital twin of the major system in air quality, in land monitoring system, and in emergency. So it's broadening the operational and demonstration products. Before a primary law at national level, at European level, can take into account a product, so a final product, to estimate, let's say, the impact that, let's say, a flooding is using, has to be collaborated and validated. This is the way that we have worked in this project, and we are working in the ERLE project. Next one. So before going in technical details, we have to take into account two major insights. So in order to have operational system, we have two major issues, two major insights. So for a constant monitoring, we have what we call the deferred time operational product. So a constant, let's say, timeline acquisition. One image every 2 days, one image every 4 days, and so on. So we set up a scheme, and also we calculate the orbits in that scheme of the satellite that allow a constant time acquisition. Then we have another issues when we are dealing with operational services. So we have to not only the emergency, but this is the most clear example, that in case of let's say an emergency, let's say also for the what is let's say flooding or subsidence issues like the Campi Flegrei, maybe you have the need of having real or near real-time products for taking decision. So you have to set up a structure, infrastructure, HPC infrastructure that is able to have the two type of part. The one that is the deferred time operational products, and a system that is allowing you to have a real and near real-time operational products. Next, and I think I will leave the floor to Margherita.
Yes, thank you, Andrea. So operationally, we develop and enhance algorithms to obtain multi-sensor Earth observation geospatial information on land cover and its changes. The land cover, that is a biophysical description of the Earth's surface, is also recognized as an essential climate variable that contributes to the characterization of Earth climate. And the representation of its complex dynamics require a huge amount of data, because we have to consider the persistence, next, okay, as well the transformation of certain land cover classes. And these two typologies of coverage are both affected by changes, like, for example, the seasonality or the phenology of the vegetation or the geophysical gradients, and the possibility also to be affected by disruptive events like fire, like floods or droughts. Next, please. So that's why, as introduced by Professor Taramelli, we talk about dynamic land cover, where the term dynamic does not refer only to a multi-temporal analysis, but to a series of products in the spatial, temporal, and thematic dimension. In fact, the dynamic length cover consists of a set of spatial and temporal thematic products whose information elements can be combined on the basis of operational requirement. And indeed, a huge data volume is needed to ensure various levels of detail. Next. As already said by Professor Taramelli, the Earth observation derived the dynamic length cover products also support application in a variety of domains, having different operational requirements from deferred to near real-time products. And these application domains range from the sustainable agriculture, for example, to support the crop monitoring or the green infrastructure and retrieval, or in the domain of ecosystem services and of environmental monitoring, for example, to underpin ecosystem service trade-off studies, or in the domain of geohazard to support, for example, the emergency service and risk assessment, as in this case in coastal area for the exposure and the vulnerability assessment. Next, please. Okay, so the overall approach essentially follows the Earth observation downstream ecosystem that Professor Taramelli has shown. That means that the satellite, hyperspectral, multispectral, and radar data from different national and international missions are provided as input data, and then processed using algorithms from the temporal and the spatial characterization of the land surfaces and related processes to first obtain what we call the intermediate products, and then to obtain towards data synergies and gap fillings a final land cover thematic product. Meanwhile, the processing chain, also the computational resources are defined in order to implement and optimize the processing chain into our HPC infrastructure. Pilot testing and gradual release of prototypes to end user are afterward integrated as pre-operational or operational products in the downstream application services from local and national level to regional and global levels. As mentioned before, we are still in the first testing stage concerning the processing of different raster data to obtain intermediate and final dynamic land cover products, exploiting the available resources and infrastructure. And today we are presenting a pilot testing considering different data input and processing to finally obtain some intermediate thematic products and monitoring some also testing variable to define the required computational resources. Next, please. So the test is performed in the area of the Kanjo Mangrove Biosphere Reserve that is located in the Southeast Asia in Vietnam, because it's a wide and highly complex and dynamic system, mostly due to an extreme rate of land use changes, mainly due to aquaculture conversion and urban development. And all these conditions are ideal for the land cover dynamic retrieval and for testing the processing chain and the required computational resources. That means, of course, a high data volume demand. Next, please. So for the testing on this area, we used two kinds of satellite data. from both active and passive sensor. And specifically, we use 9 images of coming from Cosmos SkyMed Italian Earth imaging constellation that are synthetic aperture radar data. And the image size are of SAR data are typically of the order of gigabytes, and usually the associated data volume of images stack to be processed leads to a remarkable computational demand. And we also use 2 images coming from the Prisma hyperspectral mission. That is another Italian Earth imaging mission. And the hyperspectral data are represented by an hypercube of data using a large number of continuous spectral bands defined by 3 dimensions, 2 spatial and 1 spectral. And specifically, Prisma data are characterized by 240 bands. That again means high data volume and high computational demand. So I give the floor to Serena to illustrate the testing architecture and then the preliminary results.
Thank you, Margherita. And we tested the 2 different technical configurations implemented on 2 different laptops. And here you can see the desktop specification. The laptop A have a processor of Intel Core i7 with 2.3 GHz of CPU, 16 GB of RAM, and almost 500 GB of local storage. And the laptop B, that is the higher performance machine, with an Intel Core i9 3.5 GHz of CPU, 32 GB of RAM, and almost 1 TB of local storage. All the input data, the results, and the temporary data in this case were stored and processed on an SSD drive, and variable monitored are the CPU and the RAM represented as percentage of use. The local SSD activity as byte read and written, and finally the process duration. Here you can see the workflow of the processing. We have 2 processing chains. The first one is the one implemented using the hyperspectral data. And in this case, we have several preprocessing steps, as you can see, from 1 to 5, and just 1 processing step. Just to understand the computational demanding for this step, it's important to know that we applied a sub-pixel analysis technique, which perform a spectral mixing, identifying pure elements within each pixel of the image. This first processing chain was tested on both the laptops. The second processing chain was for the SAR data, the Cosmos SkyMed data, and that were processed using SARscape Analytic Toolbox. And this processing chain was tested only on the second laptop. We performed a time series analysis, applying a tool that includes all the preprocessing steps. And for this reason, we have only 1 step. These are some examples of the intermediate thematic products provided by the processing of hyperspectral data. And these are the fractional abundance maps that represent the spatial cover composition. And this product can support the classification of the length cover. These are the results for each variable in all the processing steps. And in this case, we can see that the percentage of CPU used is very low in all the steps. And with an exception for the third step, that is the mosaicing, where the laptop A used more CPU. And we have low value also for bytes read. And this can explain by the fact that we processed just 2 images for hyperspectral data. But we have a high value for byte written. And this is due to the fact that in each processing steps, there's the generation of several temporary files and intermediate products. But interesting results are given by the RAM and the processing duration, because we can see that the laptop B always allocates more RAM than the laptop A. This is because laptop B, of course, has more RAM, and laptop A is more conservative and ties up less RAM. But from this graph, it seems that the processing duration is not affected by the amount of RAM. But this can be due to the small amount of data that we processed. But if we figure it out to process a larger raster dataset, for example, for an operational service, maybe using also in Synergy different type of data, we can suppose that the processing duration will be affected by the amount of RAM, and the computational demand will be different. Here you can see 2 examples for the SSD activity during the 2 steps, for example, the layer stacking and the mosaicing. And the laptop, you can see that the laptop A requires higher SSD activity in the final step of the process. And this is due to, this is the process where the image is wrote and visualized, while the laptop B, thanks to its higher computational capacity, can continuously write temporary files. Downstream services that require a raster-based queries necessitate specific computational resources, considering the huge amount of raster data. These are the results for the Cosmos KNet data, and we can see here some intermediate products for the time series analysis. And this analysis allows us to understand the transformation of the landscape, and this information brings us back to the concept of dynamic lane cover. It's possible. Here you can see the use of CPU and RAM storage, and you can see that this process is high computational demanding. And from the graph of the SSD activity, we can identify with the peaks several preprocessing steps. For example, the multi-looking, that is a complex computational problem due to its significant memory and computational requirements, and the image co-registration that consists in the align of 2 or more images at subpixel level, affecting the computational burning. Finally, there is the results on the comparison between SAR and hyperspectral. And we can see that the SAR processing chain transferred a large amount of data, The difference in reading and writing activity can be related to the number of image processed. Just to remind, we processed 9 images for the SAR and just 2 images for the hyperspectral. The SAR processing chain is so computational demanding compared with the hyperspectral data, and use more RAM because storage stored more temporary data. This testing allows us to define the computational demanding to implement the raster-based processing into the cluster of HPC of the use, and allow us to identify the allocation of computing requirement for also to upscaling the results of this testing, considering a preoperative service. And we haven't considered for the moment the parallelism between the operation, but this can be a step forward for the development of a high performance machine with in terms of high speed, low latency, and interconnection. And I leave the floor to Professor Taramelli for the conclusion.
Thanks, Serena and Margherita. So, as I was already introducing, it's one of the major issues that we are facing both at European level and national level is really the missing part of the HPC infrastructure for data processing. So this was a starting point in order to understand the development for operational products and improve the downstream application services. Again, a clear example is the fact that Italy is always getting the fine for the air quality issues in the Po Plain because has not set up yet an operational monitoring services using also CAMS as a boundary condition from Copernicus. So the idea is giving an infrastructure based on the Earth observation data as the European Commission and the framework directive of the air quality is asking since almost 15 years to Italy. Of course, availability of suitable IT facility is one of the becoming increasingly important issues, and still European countries and Italy has not yet been there. So we are really using a lot of like Microsoft and so on. So the Commission with the DG Connect and DG DEFIS is really pushing member states to figure it out how we can do that. And it's important that all these requirements can be made only if you test specific consolidated algorithm that can really produce operational data information based on different type of data. As Serena was well presenting, you have 2 different type of processing. While the SAR data that has like coherence and amplitude of the data of the information has a specific issues that has to be taken into account. With the hyperspectral data, we have to consider that we have more or less 240 bands to deal with. So even if we have only 2 images to produce a data, we have 240 space dimension that we have to take into account. So the testing is really important, and let's say the take-home message is we are still at the beginning, at least at European and national level in that sense, and we are happy to share the experience. For any question, we are here to answer. Thanks a lot for inviting us. We have already some publication and other publication are on the way. The first one was just published last week.
Thank you.
Time for questions online or in the audience. Which kind of cluster you have installed in Pavia?
This one.
Yes, this is
It's a high performance computer clustering, and you can see here the resources. And we built this cluster with on the basis of the results of this study. And so we had 32 core CPU, 128 gigabyte of RAM, and so on. You can see here the specification of the cluster.
the total is 700. How many teraflop?
Yeah, I don't know.
Yeah,
really.
700.
700.
That's the starting point. Actually, this is just for not even pre-operational products because it's not facing other issues as Margherita and Serena were saying. So this is the base. So in this case, if we start to, let's say, download and archive Sentinel data, is not enough. It will be saturated shortly. So it's completely not enough.